Hello, good morning, good afternoon, and good evening to partners and friends. My name is Denise from the Climate and Clean Air Coalition Secretariat. Welcome to the first of the two-part webinar series titled The New Cool Alternative Cooling Technologies, organized by the Carbon Containment Lab, RMI, and the CCAC. I'll take off my sunglasses because I can't see very well now. Trying to be cool here. But again, welcome to all of our partners and friends. This series of webinars brings together innovators, analysts, and technical experts to demystify alternative cooling technologies, or ACTs, showcase breakthrough technologies, and explore the market and policy levers needed for global deployment. Today's first session is titled Deep Dive into Active Cooling Technologies and Market Levers to Scale Acts, and will be introduced in more detail by our friends from the Carbon Containment Lab. We invite everyone to introduce yourselves in the chat, your name, your organization, and your current location or country. And for questions during the webinar, you can type them using the Q&A function of this webinar. With that, I'd like to hand over the floor to the amazing Anastasia O'Rourke, Senior Managing Director of the Carbon Containment Lab and lecturer at Yale University. Anastasia, over to you.
Thank you, Denise, and hi, everybody. Thank you so much for joining us today. We're really excited to share some initial overview of alternative cooling technologies, some research that we've been doing at the lab, and just have a good discussion with everybody about what can be done to help these come to market and really succeed in the world. So what I'm going to do is, first of all, kind of bring us from very high level into why are we even caring about alternative cooling technologies, and what is the problem we're trying to address with some of these. And then my colleague Celine Goren will explain what are they, what are the different types, and then we've got a really great program today with several great examples of alternative cooling technologies. We also have some reflections on what's happening in this particular space from RMI, from Lindsay Rasmussen. And then we'd love to have a Q&A dialogue as far as we're able to through the Q&A function and the chat, and we'll try to get some questions and answers towards the end and then wrap up. So that's our program for today. So let me start by saying cooling, the need for cooling is really growing as the world warms, as well as, as countries and people are developing around the world, and as we're urbanizing, we're seeing just a massive projection for the need to cool both our buildings and ourselves in our buildings, as well as our food, our pharmaceuticals, and all sorts of industrial systems that use cooling technologies. Here's a projection from the IEA on the future of air conditioning units, and where in the world they're likely to be fastest growing, which is, outside of the US where I'm sitting today. There's expected to be massive growth. And this is, in many ways a great thing, because we want to address everyone's comfort and health as the world warms and becomes more humid. But unfortunately, with the existing suite of technologies that we're using to provide this cooling, this is starting to become a big problem from a climate change point of view, and I'll explain why. But also because of the energy use that will be needed to power all of these systems. So looking ahead, let's think about not only our existing technologies, but also what alternatives are needed. You can go to the next slide. Thanks. So what is the nature of the problem with the existing technologies? As I said, many of these use a lot of energy, but in addition, many of them use fluorinated gases, and these gases are what's starting to be called super pollutants. And part of the reason they're so potent in the atmosphere as greenhouse gases is because they're very effective at trapping heat. This is why we use them, in fact, for cooling technologies. And they're also very persistent in the atmosphere. So some really interesting work is coming out recently, really showing that some of these super pollutants, including HFCs or these fluorinated F gases, but also methane and black carbon and N2O and others, combined are responsible for around 45% of global warming to date. So much bigger than what people think. Now, these gases they behave differently than carbon dioxide. They don't hang around in the atmosphere for as long in general. So that's actually a good thing, because if we can reduce them from being emitted to the atmosphere, then we have a chance of addressing global warming in the near term. So can you go to the next slide? Thanks. So one of the things that we're thinking about at the Carbon Containment Lab, and many others are as well, is thinking about how can we ensure that some of these HFC gases in particular do not enter the atmosphere. And while the Montreal Protocol has been extremely successful in limiting the upstream production of both ozone depleting gases and the really highly potent greenhouse gases of the HFCs, there's still this big bank of refrigerant sitting in equipment all over the world. Unfortunately, it's slowly leaking, and then at end of life, when the equipment goes to is no longer in use, oftentimes that those gases are released to the atmosphere. And so and many others are thinking about life cycle refrigerant management. How do we manage this big bank of gases so that they do not enter the atmosphere? What can we do to make sure we recover them, we reclaim them and reuse them where we can, or we destroy them and we just stop them from entering the atmosphere? But in addition, if you think bigger picture, we want to think about what else can we be doing here beyond managing these gases. We don't want this problem as a society long term. There's got to be some better ways. So could you please go to the next slide? So the Carbon Containment Lab, just very briefly, we're a non-profit. We are based in the USA. We're very tied to Yale University. We're part of Yale, now we're independent. And we've taken a real interest in HFCs and super pollutants. You can see some of the photographs here show that we really love getting out into the field. We love actually understanding the realities of how do you get these gases out of equipment, move them here, destroy them there, recycle them, and so on. And there's many lessons learned from that. In addition, we really like seeing the new technologies. And so our function as a lab is to shed light on what's possible and to help to remove some of the bottlenecks that we see out there, either in the policy space or regulation, looking at investments, thinking about what can really be done. What can we do to shed light on this? So that's just a little bit about us. But we've taken an interest in alternative cooling technologies, and I'm really happy to hand over now to my colleague, Celine Goren, who's leading our work on this, to explain what are these alternative cooling technologies and why are they so important. So Celine, over to you.
Thank you, Anastasia. Hello, everybody. My name is Celine Goren, and I'm leading our alternative cooling technologies workstream here at the Carbon Containment Lab. As Anastasia mentioned, to mitigate the climate impacts of super polluting refrigerants, industry, civil society, and policymakers are considering many different alternatives, including the phase down of high GWP refrigerants as dictated by the Kigali Amendment of the Montreal Protocol, the life cycle refrigerant management of the existing bank of refrigerants, and also accelerated adoption of low or zero global warming potential refrigerants. But these approaches, as we know, are all crucial and indispensable tools in our toolkit. But we also know there's no one size fits all when it comes to decarbonizing the cooling sector. And we shouldn't limit our thinking to the existing suite of technologies. This monumental problem of decarbonizing cooling sector requires a complete portfolio of solutions with an eye toward innovation. That's where alternative cooling technologies come in, or ACTs, as we shorten them. These technologies provide cooling without relying on vapor compression and eliminating the need for refrigerants altogether while achieving higher energy efficiency. In fact, the idea of alternatives is not new to the Montreal Protocol community. As you all know, the role that in-kind substitutes played in the phase out of ozone-depleting substances sets a really compelling precedent for the role that ACTs can play in the HFC phase down. So as I mentioned, we define ACTs as cooling systems that achieve the same effect without relying on vapor compression. So these systems go beyond or replace significant aspects of the conventional vapor compression cycle, which relies heavily on these superpolluting refrigerants. And ACTs encompass active, passive, and hybrid cooling systems as we categorize them. So now I'm going to walk you through the different categories of ACTs. So as you can see here on the screen, we as the CC Lab categorize ACTs into three main buckets: passive cooling, active cooling, and hybrid cooling. In today's webinar, we will focus on active cooling solutions, but we also have another webinar coming up next week where we'll dive deeper into passive and hybrid solutions. So to give an overview, active cooling solutions use electrically or mechanically driven processes involving advanced materials. These include solid-state cooling solutions, which are the most popular solutions in this category. We have elastocaloric systems that generate cooling through stress-induced phase transition of shape memory alloys. Then we have barocaloric systems that exploit pressure-induced thermal changes in solid-state compounds. Magnetocaloric systems utilize magnetic field-induced entropy changes in specialized materials. Thermoelectric systems use electric current to create a temperature gradient across semiconductor junctions, utilizing the Peltier effect. In addition to these solid-state technologies, we also have other technologies such as thermoacoustics. These use sound waves in gas-filled chambers to generate temperature gradients. And then we have air-based, which use air, actually, as the working fluid, providing refrigerant-free cooling through compression and expansion in a closed loop. As I mentioned, for passive and hybrid, we have a whole another webinar coming up. But to give an overview of, there are these different categories that we use to categorize passive and hybrid solutions. And in general, passive cooling doesn't rely on energy input, and hybrid cooling has components of both active and passive cooling. So we created a new category for that. And as I mentioned, we will dive deeper into those. So we are really excited to introduce you to some of the amazing ACT innovations out there today as part of our webinar. But of course, we know there are many more out there than we can fit in a single webinar. So we built a database for you to go explore them on your own time. And this is, of course, just a start. We're actively looking for other pioneering technologies. We would love to get your inputs as well as we expand this database. You can check out the database here by scanning the QR code, and you can explore the technologies. And as I mentioned, if you know of others, please reach out. I'm actively building out this database, and we would love to add after today's webinar, which of these technologies spark your interest the most and what applications you think show the most promise. We would love to hear from you. Also, it's important to note that in this webinar, while we're exclusively featuring startups, original equipment manufacturers also have a big role to play to help commercialize these technologies by offering access to established distribution networks and manufacturing infrastructure that they already have. So although we're highlighting startups, we also would like to emphasize that OEMs have a big role to play here. And we hope they're also working on the next generation of systems. My greatest takeaway from this research on ACTs is that there's a breadth of promising technologies out there emerging globally, and these innovations are no longer confined to the lab. They're already out in the world. We're at a tipping point where stronger policy and financial support can actually help scale these technologies, and they can move from lab to market, as Lindsay from RMI and Third Derivative will explain today. We'll dive deeper into the commercialization aspects. And we think the Montreal Protocol community has a huge role to play here in making alternative cooling technologies an integral part of this cooling portfolio that we talk about today. So this is a non-exhaustive list of technology companies that we mapped. All of these are included in our database as well, plus some others in our database. Just to illustrate what the landscape looks like currently. And now we will look into, we'll dive deeper into 4 of these pioneering solid ACT examples. And we selected these to give you a glimpse of what is out there and how technologies work. I'd like to point out that we don't have any relationships with these companies, financial relationships, nor do we endorse them necessarily. They're meant to be examples and illustrate what ACTs are. As you watch these videos, as Denise mentioned, there's a Q&A feature portion at the end of the webinar. So please put in your questions using the Q&A button. And we will have the ACT developers that we're featuring here today with us. They're in the audience right now, and they will join us for the Q&A to help answer your questions. So please send them to us as you watch the videos. So first off, we have Exergen. Exergen is a solid-state cooling company which uses elastocalorics. Exergen's technology exploits the temperature change that occurs when shape memory alloys, such as nickel titanium, are mechanically stressed and released. This creates a temperature change, eliminating the need for traditional vapor compression refrigerants. Exergen has their HQ in Ireland, with facilities in the UK and Czech Republic. They're in the process of commercializing their next generation heat pump systems, and their technology applications include HVAC, refrigeration, and transportation, so quite a range. So now we're going to hear from Kevin O'Toole from Exergen.
Hi, I'm Kevin O'Toole, CTO and founder of Exergen Limited, and I'm excited to share how we're working to decarbonise heating and cooling at scale. Exergen aspires to address one of the toughest climate challenges, heating and cooling. Globally, heating and cooling accounts for over half of energy use, and most of it still relies on fossil fuels and/or the use of refrigerant gases with exceptionally high global warming potential. Our bold vision is to develop a radically different kind of heat pump, one that uses a solid-state refrigerant with zero global warming potential and can compete on key metrics such as performance, cost, safety, size and weight. That's what the end user cares about, and it's what drove us to pioneer a solid-state heat pump based on shape memory alloys, specifically the superelastic effect. We're headquartered in Dublin, Ireland, with additional R&D and materials development facilities in Rugby in the UK and Prague in the Czech Republic. Our team of nearly 50 highly skilled individuals combine deep materials science with thermal systems engineering to build scalable, manufacturable, clean heating and cooling tech. At the heart of our elastochloric heat pump is a smart material called a shape memory alloy. These metals change shape when compressed and relaxed, undergoing a solid-to-solid phase change. That's what drives the heating and cooling. It's similar in concept to how traditional heat pumps work, where they cycle refrigerant gases between a liquid and vapour phase, but with one major difference: gases leak. Whether it's during operation or at the end of life, refrigerant gases tend to escape, and many of them are highly potent greenhouse gases, thousands of times more powerful than CO2 at warming the planet. With shape memory alloys, that problem disappears. They stay solid, so there's nothing to leak. Our system uses a simple mechanical drive and transfers heat using water or a water glycol mix. There's no flammability, there's no toxicity, no traditional compressors, just clean, efficient, safe and controllable heating and cooling. Our technology is built as a platform that can adapt across the full HVAC spectrum and even beyond. It operates efficiently as low as -50 degrees Celsius and up to 140 degrees Celsius, giving it a much wider temperature range than conventional heat pumps. That makes it suitable for everything from refrigeration, space cooling, residential and commercial heating, industrial heat pumps, and even high temperature process heating. It's especially valuable in markets transitioning away from gas boilers, where there's a real need for high grade heat, something traditional heat pumps often can't deliver effectively. We've successfully run full-scale heat pump modules for over 24 hours straight, delivering up to 60 kilowatts of heating. In 2023, we operated a 10 kilowatt system within a typical low temperature heating range, that is between 7 to 35 degrees Celsius. And in those trials, we achieved a coefficient of performance, or COP, in line with an equivalent R134A system. And there's still plenty of room to improve as we refine both the materials and the system design. The systems currently in development are targeting operational ranges between -10 Celsius to +70 Celsius, with seasonal COPs in some cases up to 10% higher than today's state-of-the-art heat pumps. We're working closely with manufacturing partners now, aiming to bring our first commercial units to the market later this decade. At Extrogen, our mission is straightforward: to build heat pumps that are cleaner, simpler and truly scalable, without compromising on what matters most to end users. That means strong performance, competitive cost, safety and compact size and weight. We believe solving for these real-world issues are the key to driving mass adoption, and we're very proud of how far we've come and even more excited about what's ahead. We look forward to continuing to engage with the Montreal Protothal community through the Alternative Cooling Technologies Policy Framework. Thank you very much for your time.
Right. Thank you, Kevin, for that message. Next up, we have Magnetherm. Magnetherm is a solid-state company using magnetocalorics. They are headquartered in Germany. Timur Sirman is actually with us in the audience today, so he'll be able to answer your questions. I also saw he was saying hi in the chat. Magnetherm systems utilize reversible entropy changes in magnetically active materials like gadolinium when exposed to magnetic fields. This enables refrigerant-free cooling with high temperature differentials and achievable in compact systems. They're developing magnetic beverage coolers and refrigeration units for retail to begin with, but they have plans to expand beyond that to hydrogen liquefaction and data center cooling in the future. Now we'll hear from Timur Sirman of Magnetherm.
Hi, I'm Timur Sirman, CEO and co-founder of Magnetherm. Magnetherm is headquartered in the greater Frankfurt city area and was founded as a spin-off from the Technical University in Darmstadt. We are a team of 35 and we operate our systems mainly in Europe with a global expansion plan. Our vision is to shift the cooling industry towards refrigerant-free alternatives to make cooling safe, clean and energy efficient. We aim to establish the magnetic cooling technology as a better alternative to gas compression and optimize it for mainstream market adoption. Our refrigerant-free cooling technology harnesses the magnetic caloric effect of certain metals and alloys, which heat up when they are exposed to a magnetic field and cool down when the magnetic field is removed. The core of our systems are our proprietary alloys composed of lanthanum, iron, silicon, and manganese, which are used to achieve custom temperature spans through the AMR, the active magnetic regeneration process. The alloys are placed within our AMR modules, which are located between two rotating discs of permanent magnets. By rotating the permanent magnets, the alloys undergo continuous magnetization and demagnetization. We are entering the market in the commercial refrigeration space, where we refrigerate foods and beverages. With Polaris, we have introduced in 2022 the world's first commercially available magnetic beverage cooler. With a cooling capacity of up to 100 watts, it has been successfully operating in several FMCG retail stores. In 2024, we introduced the Eclipse platform as an integratable cooling unit, delivering up to 1 kilowatt of cooling capacity. In 2025, we expanded our product portfolio with the Eclipse 2D, a two-door magnetic refrigerator, and with the Eclipse TL, a top-loading refrigerated island unit which has been successfully undergoing field testing for several weeks in supermarkets with a technology readiness level of 7. The Eclipse TL has a temperature span of 26 Kelvin and can cool down food and beverages below 5 degrees centigrade. It has a cooling capacity of up to half a kilowatt and operates typically in steady state mode at 0.25 kilowatts. It has a COP of 2 measured under standard operating conditions and a COP of 3 under lab conditions. Leveraging our future platforms with potential cooling capacities of up to 500 kilowatts, we will enter cooling applications for buildings, data centers, and industrial processes.
Thank you, Timur. If you have questions for Timur, please drop them in the Q&A. We're going to address them as many as we can. Next up, we have Pascal, which is a solid-state cooling company using barocalorics. Pascal develops barocaloric cooling using pressure-induced solid-state phase transitions to transport heat, eliminating refrigerants and enabling compact designs. Operating within standard HVAC pressure and temperature ranges, barocaloric systems are suited to small and medium-scale cooling. Pascal is headquartered in the US and has developed special barocaloric refrigerants using metal halide perovskites, and they're scaling from laboratory validation to commercial demonstrations. Their technology can be applied to anywhere from residential and commercial HVAC, and as well as refrigeration, although their focus to begin with is on commercial refrigeration. Now we're going to hear from Adam Slevny of Pascal.
Hello, I'm Dr. Adam Slevny, CEO and co-founder of Pascal. We're on a mission to reimagine cooling without the climate cost. Traditional vapor compression refrigerants have cooled our spaces for over a century, yet each new synthetic version has proven harmful to our planet and human health. Many new alternatives are expensive or raise concerns about efficiency and flammability. With refrigerant leaks still contributing to 3% of global emissions, it's clear traditional vapor compression systems are long overdue for an upgrade. We aim to build a truly future-proof solution. At Pascal, we're developing the world's first alternative cooling technology that's more energy efficient, non-toxic, non-flammable, and costs the same as current systems. And how do we do it? Through a breakthrough in solid-state cooling. After a decade of research at Harvard University's Department of Chemistry in Boston, USA, a groundbreaking experiment from my co-founder, Dr. Jin-Young So, led us to realize that we could do solid-state cooling in a new way with new materials, barocalorics. We founded Pascal to commercialize this breakthrough and are working to showcase our demo system in November of this year. Barocalorics work by absorbing heat when you apply pressure. While vapor compression systems compress a gas into a liquid, our system compresses a disordered solid into an ordered solid. This creates a solid-to-solid phase change that produces heat. Barocalorics are a truly safe, low-cost, and higher efficiency alternative to traditional refrigerants. Our materials are completely non-toxic, non-flammable, contain no PFAS, and are readily available from existing supply chains. We buy them and then apply our proprietary processing techniques to unlock their full potential. Pascal's proprietary system design incorporates almost entirely off-the-shelf components sourced from the existing HVACR supply chain. We assemble these components into a unique configuration, incorporating our low-cost solid refrigerant materials. This configuration allows us to achieve cost parity with existing vapor compression systems. Because our solid refrigerants have 40% greater energy density compared to conventional gas refrigerants, we are anticipating at least a 20% improvement in energy efficiency over today's best-in-class vapor compression systems. We are currently working to show this efficiency in a full-scale demonstration system completed in November. While our technology can be used for both heating and cooling and is competitive across most product categories, including air conditioning and space heating, our first focus is the global commercial refrigeration market. We aim to demonstrate a first-of-a-kind 1 kilowatt commercial refrigerator this November. Our demo will have a temperature span of 5 to 35 degrees Celsius with an efficiency that equals or outperforms current vapor compression systems. We are currently in discussions with potential commercial refrigeration customers to bring this product to market over the next several years. As global temperatures rise, cooling is no longer just a comfort issue, but a human health necessity. To address this crisis, Pascal is bringing solid refrigerants out of theory and into the real world. We are on a mission to create the next generation of cooling without harming the planet. Join us.
All right, that is a great motto indeed, and great aspiration for all of us. So last but not least, we have Mimic, which is a solid-state company using thermoelectrics. Mimic designs solid-state heating and cooling systems at building scale, leveraging thermoelectric technologies to replace conventional HVAC systems. Their systems use no refrigerants and involve virtually no moving parts, resulting in lower maintenance and quieter operation and fewer sources of mechanical failure. Because there's no compressor, their solutions are silent and vibration-free and more comfortable in settings like homes, small commercial spaces, or sustainable building retrofits. Mimic aims to make electrified solid-state heat pumps as a practical, sustainable alternative for heating and cooling of spaces. Mimic is headquartered in the US, and their primary application is in residential and light commercial HVAC. Now we're going to hear from Berardo Matalucci of Mimic.
The semiconductor industry has transformed our lives, from computing to solar energy, displays, and communication. At Mimic, our goal is to enable that same transformation for heating and cooling. My name is Berardo. I am the CEO and co-founder of Mimic. The HVAC industry has a technology problem. It relies on compressors and refrigerants using harmful pollutants that are expensive and difficult to maintain. At Mimic, we have developed a system for heating and cooling using solid-state technology. Instead of using refrigerants, we use semiconductors to move heat. leveraging a phenomenon called thermoelectric energy conversion. Essentially, we use electrons to move heat rather than liquids. Our core technology comprises of two parts: a modular heat pump that physically delivers heating and cooling without any moving parts, and a smart control board that digitally operate our modules. Depending on how we package those two elements, we can put them in a variety of different markets, including buildings, appliances, and beyond. So how do we start? We know that the electrification of existing buildings is a major problem in every city. Property owners are struggling to electrify and move to all-electric heating and cooling while reducing maintenance costs. And this is where we can come in. Our technology solution is easy to install, compatible with existing systems, maintenance-friendly, and emission-free. We have developed a terminal solution like this one that provides enough heating and cooling suitable for apartment buildings and hotels. Today, our systems already achieved efficiencies equivalent to traditional heat pumps. As we implement the new thermoelectric materials, we know that we can surpass them. We have paid pilots on the way and rapidly moving towards commercialization. At Mimic, we want to lead the transition from refrigerant-based HVAC to solid-state heating and cooling. If you want to be part of it, reach out to us.
So this concludes our videos submitted by our wonderful ACT innovators. And now I would like to invite Lindsay Rasmussen of Third Derivative to give us her and her team's analysis of commercialization of ACTs and how to bring these great solutions from lab to market and scale them.
Perfect. Thank you, Selin. So by means of introduction, my name is Lindsay Rasmussen. I'm a manager on Third Derivatives research and diligence team, and I lead Third Derivatives building sector efforts more broadly. We can go ahead and go to the next slide. And maybe just to introduce RMI, or Rocky Mountain Institute, we're a global nonprofit focused largely on energy and climate. We anchor our work with techno-economic assessments, focused largely on market-driven solutions, and we work across every sector relative to the energy transition. RMI launched the Third Derivative program back in 2020, building off the realization that 35% of the technologies we need to get to net zero weren't commercially available. They're still in prototype or demonstration phase. And unfortunately, we don't have decades for these critical climate solutions to get to market and get to scale. So Third Derivative's core mission is to scale climate solutions faster. And we do this primarily through an accelerator program that we supplement by research and projects that help prime the market for tech adoption. Just a couple stats here. So since launching in 2020, our portfolio has grown to include 286 startups developing these critical climate technologies from 27 different countries. We support these startups by leveraging the expertise of RMI, which is over 700 subject matter experts globally, as well as about 220 external mentors worldwide. We also connect our startups to corporate and VC partners for investment. The partners we're most connected to have over 4 trillion in market capitalization and about 12 billion in assets under management. And as a result, our startups have collectively raised over 3.8 billion since we launched. But more importantly, they've about a third to date have now reached commercial stage. Next slide. So one key area of focus for Third Derivative and for RMI more broadly is cooling. As Selin and Anastasia shared earlier, cooling is responsible for a large percentage of global greenhouse gas emissions. It's also a key driver for electricity demand growth globally. Cooling demand is increasing with higher temperatures, with growing populations, as well as with growing incomes in really heat-stressed regions. So to significantly reduce these growing cooling emissions, we need both evolutionary and revolutionary innovations. And our work focuses on both. So as Selin introduced, or Anastasia introduced, these evolutionary innovations are improvements to existing vapor compression systems, which includes things like low GWP refrigerants, improved efficiencies, improved compressor technology, and things like new coatings for heat exchangers. The industry in the last decade or so has really focused largely on these low GWP refrigerants, or looking at alternatives. And unfortunately, those are also facing some pretty big challenges, including things like flammability, toxicity, and cost. However, these types of innovations are really critical, since 95% of all cooling equipment today utilizes vapor compression cycles. However, as we look forward, we really need to look at what we call these revolutionary technologies, or what we here today are calling the alternative cooling technologies, which I really like that phrase as well. And as was introduced, these are the non-traditional approaches to cooling that can deliver significant efficiency gains. This includes the hybrid approaches that Selin introduced, like liquid desiccants, metal organic frameworks. On the active cooling side, it also includes things like solid state cooling. So as has been introduced, solid state cooling uses solid materials to facilitate heat exchange, eliminating the need for refrigerants, which is a key advantage of this technology class, as it can reduce the climate impact, but it also mitigates current and future regulatory constraints that customers might be facing on refrigerants. Other advantages, as we've heard already, include efficiency gains that can potentially surpass vapor compression systems, as well as user benefits like silent operation, modularity, and precise temperature control. Next slide. So just speaking to these efficiency gains, there's a lot of potential with solid state cooling to produce highly efficient systems. As the key driver is, it's not dependent on moving heat between reservoirs, as vapor compression cycles are. In the HVAC space, efficiency is often measured by what's called coefficient of performance, or COP. And though this is not a perfect measurement of a system's efficiency, essentially what this is showing is how much heat or cooling a system can produce per unit of energy it consumes. The average AC on the market, as you can see here, is close to about COP at 8. There's a bit of a range there, or sorry, COP of 3. There's a bit of a range there. But best-in-class ACs on the market are reaching COPs closer to 5 and 5.5. So solid-state companies, especially researchers, have shown COPs above 10 and even 15 in lab settings for solid-state components specifically, which is incredibly exciting and speaks to the potential of this technology class. However, it's important to note that those components are just one piece of larger cooling systems. So as you integrate that component into the larger cooling system, you tend to lose some of those efficiency gains. And this means that we'll likely see solid state cooling technologies that are closer to or above at market vapor compression technology, or even closer to that best in class threshold as well. And this is exactly what innovators are focusing on right now, is translating that potential into reality. We can go ahead to the next slide. So we've heard from several solid state cooling technology developers today, and just to give a sense of where they are generally in development, generally magnetocaloric and thermoelectric are the furthest ahead. They're leaning on a lot longer history of research, and these startups are now in kind of early pilots, early commercial stages. Then elastocaloric and varicaloric are newer classes to be researched, and so startups here are largely in prototype development or early testing phases. Next slide. As we've heard from these solid state companies, as well as from Selin and Anastasia, each of these solid state technologies has its own key benefits, as well as its barriers or challenges to scale. So for magnetocaloric, which again uses magnetization and demagnetization to transfer heat, they're the furthest ahead. They offer really high cooling capacities and COPs, or efficiencies. But some of the challenges here for them are working to address the cost of the materials used and establish supply chains for some of those critical components. For thermoelectric, which uses electrons to transfer heat, benefits here are compact sizes, modularity, very precise temperature control, silent operation. As Berardo shared, thermoelectric has really evolved from computer applications or chips, and so it's been scaling up over time to address like room air conditioning. And so as a result, increasing that cooling capacity without increasing cost is currently a focus of these technology developers. Elasticaloric and bare caloric are similar in terms of their benefits and barriers. So both of these have incredibly promising performance metrics. But one of the barriers is that they both require repetitive motion, either compression and decompression or stretching and release. And so the system itself has to overcome challenges with fatigue. So developers here are really focused in on kind of system optimization, as well as fatigue challenges with that system. But there's been a lot of incredible progress recently, which is exciting to hear. Next slide. So as these challenges are overcome, the exciting news is that, I mean, beyond the excitement of what solid state technology is in general, one exciting piece is that the market potential for these technologies is huge. The global cooling market is large enough and even segmented enough that solid state cooling startups can find sizable beachheads or starting markets. So for example, Mimic, which we heard from today, which was Berardo who presented, they're one of D3 portfolio companies. They're focused on developing essentially PTAC units or packaged thermal air conditioning units. If you don't know what that is, if you think about like a hotel room or a multifamily housing, that's kind of the system you typically see there. If, for example, Mimic were to focus solely on addressing hotels as a market, in the US alone, that could be a $7 billion market. For Magnotherm as another example, they're based in Germany. They're really focused on refrigeration. So refrigerators for supermarkets, grocery stores, food and beverage, et cetera. In Europe alone, that market is estimated to be about $17 billion. So really large, really sizable segmented opportunities for these startups. And as I think Anastasia mentioned super early on, we're actually seeing the greatest market growth in emerging economies too. So emerging economies will make up about 60% of the global cooling market growth to 2050. Next slide. So getting these startups to market, they do have a really strong tailwind or a thing that's helping to push them to adoption faster. And one of those biggest tailwinds is actually policy and regulation. So this includes policies that constrain the use of high GWP refrigerants like the Kigali Amendment, the AIM Act in the US, as well as EU's F-gas regulations. This also includes regulation or policy focused on energy efficiency or minimum energy performance standards like Japan's Top Runner program here is a really great example, things that can play a really critical role in lowering emissions while also driving economic savings through improved efficiency. And then finally, regulatory things like Global Cooling Pledge, which is not necessarily regulation, but it is a large commitment and requires 68% or greater reduction in cooling-related emissions by 2050. And that's targeted at both government level, sub-government level, as well as non-state actors. So a pretty broad global commitment. Next slide. So there are also headwinds or barriers to adoption that solid state cooling startups need to overcome. Primary among these is upfront cost, and this applies across the spectrum for climate technologies, but for cooling specifically, the sticker price is a major consideration. So solid state cooling startups are going to be higher cost upfront, but this will decrease in time as they optimize their systems, as well as they produce more at scale. You reach economies of scale. So in the meantime, this is where things like rebates or incentive programs can really help a lot in overcoming that first cost hurdle while these startups are scaling up. Some other notable challenges include gaining enough investment interest to help progress their development over time. Risk aversion, largely from the building sector. The building sector is notoriously risk adverse and really hesitates away from adopting unfamiliar technology. So this is something that can be mitigated by the development of drop-in solutions or things that are easier one-to-one replacements for existing systems, as well as through things like just customer education and awareness. For some solid state cooling technologies, supply chains will need to be either established or ramped up in order to support their growth. So that's something that a lot of them are addressing as well. And then the last one I'll mention here is just that the cooling market itself is quite consolidated. So that means that there's a few major players like manufacturers of HVAC equipment that really dominate the market. And this is where engaging with those developers can be really essential to growth and to the exit strategy for these startups. Next slide. Great. And just to wrap up, I wanted to share a bit more of a qualitative perspective on the path to market for these companies and what it will, likely take for success here. So right now, many startups are in this first refinement and validation phase. This requires continued funding for research and development, as well as early engagement with building sector or architect, engineering, construction, AEC folks, and perhaps even early engagement with industry players or HVAC manufacturers. The second phase here is validation, and this is really critical. This is where startups need to demonstrate that their technology works in real-world environments. To support those pilots, startups need to have enough units to pilot, which means setting up pilot manufacturing lines. In order to get pilots, they need to increase market awareness. And I'll say that's something like this event can actually help a lot in. So shout out to the Carbon Containment Lab for helping organize this. And then I'll note that this validation phase is also the cusp of where standard development starts to become important. So it's important to note here that standards for cooling equipment were built around vapor compression systems. So the codes, incentives, certifications, those are tailored to vapor compression and don't necessarily make a great fit for startups in solid state cooling. So if these bodies can get ahead of this and develop things like performance-based standards or include solid state as an option in certifications like LEED, that can go a ways in supporting the growth and adoption of these technologies. And I should actually note on that too, that developing economies have a really huge opportunity here to leapfrog developed economies like the US and the Europe, because we're using largely outdated standards. And so there's opportunity, again, to leapfrog by developing those performance-based standards that can really help in the advancement of highly energy efficient technologies that are outside what's traditionally accepted within code. And then, so once validated, startups need market demand for their product. And we're seeing this a bit from players like Walmart and IKEA, who have refrigerant or cooling efficiency goals, but there's a lot of opportunity for leadership, both from private and public players here. Private sector leaders can support demand by establishing things like advanced market commitments, buyers platforms, as well as even internal corporate commitments like Walmart and IKEA have done. So the private sector support can really boost demand again. And then public sector can support that by establishing standards that incorporate solid state as an option. And then finally, partnership. So once the technology has been validated enough and there's clear market demand, startups will likely license their technology to or do a joint venture with OEMs or HVAC manufacturers. They could sell key components to these OEMs or even be acquired by the OEMs. So there's a lot of pathways there for further scaling, leveraging that OEM's manufacturing capabilities, as well as name brand and customers globally. So as I mentioned, I think on the last slide, the cost of these systems is of course higher now, but this will drop with system optimization and higher volumes of production. That requires both validation and market demand. On performance, we expect performance to increase over time as these systems are optimized, and even potentially through further advancements in material science development. And of course, while all of this is qualitative, what we do see is that the scale of adoption for solid state, which is the two dark blue lines here, this will be largely influenced both by regulation, by standards development, as well as by continued investment in grants for R&D by solid state startups. So I'll end by saying that for those of you on the call today, regardless of where you are, if you're a policymaker, if you're a corporate HVAC manufacturer or even an investor, there's a lot of opportunity for you to engage with and support the growth of this really compelling technology class. So I'll wrap with that and really happy to answer any questions you might have.
Thank you so much, Lindsay. So now we'll move on to the audience Q&A portion of the webinar. We already got some questions, and feel free to ask more as they come up. We'll answer as many as we can. So the first question is actually for Magnetherm and Pascal, and we have representatives from both companies here with us today. So I might call on Timur to begin with, actually, to help me answer this one. Tori is wondering why Magnetherm chose the segment of commercial refrigeration for your market entry. So Timur, if we can unmute you, or you can unmute yourself if you want to take this one.
Yes. Hi, great to meet you all. Thanks for this question. It's actually a very good question. So why did we choose this market segment for our market entry? So it's a combination of two things. First of all, it's a B2B sector. So we are not entering B2C for many reasons. This specific B2B sector also looks a lot on the running costs, on the operational costs, including energy consumption, but also maintenance. So another benefit from our refrigerant-free cooling technology with magnetocalorics is that it's a lot easier to maintain without the standards and the regulations that are needed for example, natural refrigerants, which can be explosive or harmful in any way. So that's one of the reasons. And also technically speaking, it's a low-hanging fruit for us because the temperature differences are quite small. And also there's a wide range of applications within commercial refrigeration, starting from on top of the counter refrigerators to plug-in units, which come in different forms and shapes, all the way towards a whole supermarket that needs to be refrigerated. So within this sector, there's a lot of applications that we can grow into. And having this customer relationship already established is just very interesting for us from a business perspective as well.
Oh, thank you, Timur. Victoria, do you also want to answer this one on behalf of Pascal?
Sure, great. Hi, I'm Victoria Marquez, the head of business development for Pascal. And just to add on a few things to what Timur said, I think one of the main reasons we chose refrigeration is because when you're choosing your first customer segment, you ideally want a customer that's already looking for your solution before you try to sell them the solution. And when it comes to refrigeration, that customer segment has been facing the regulations on changing refrigerants for decades. They have been forced to switch their systems several times to accommodate new regulations. And so when you say, hey, I've got a solution that's future proof, that would be zero GWP and you wouldn't have to deal with these regulations, that would be something that would solve a lot of future spending for them. It's something that the customers in the refrigeration area really look to. And I think those regulations are a bit more advanced than they are in HVAC. And then on the other hand as well, another reason why refrigeration is more interesting is when you think about the market for HVAC versus the market for refrigeration. For HVAC, when you sell an HVAC unit, you might need to go through an OEM or a distributor or a contractor before you finally get to the customer. Whereas with refrigeration, you're more directly in touch with the customer. And so you can make your case directly to them and say, here are all the environmental benefits, here are all the system benefits, here are all the maintenance benefits. And that customer, like a grocery store chain, would own multiple units. Whereas when it comes to HVAC, even if it's someone like a chain that owns a lot of buildings, you would have to make your case building by building, and you would have to adapt the system to what that building needs. Whereas in the refrigeration section, they're more segmented markets that have similar products, and you can speak directly with the customer. And when there's such a high value that we're trying to share, this value of no PFAS for future proof against regulation, non-flammable, we want to make sure that we're directly making that pitch to the customer.
All right, thank you both. While I have you both here, actually, another technology specific question from Vivian Blake, who is from the National Ozone Unit of Jamaica. So Vivian is wondering if there are any waste management issues with respect to the cooling matrices being used for the technologies.
So I can take this. So inherently, since we have a solid state refrigerant, so to say, which is a metal in our case, it's quite easy to recycle it, to reuse it. So at Magnetherm, at our company, we have a technology which makes those materials long-term stable, and this enables us now to commercialize also magnetocalorics and make it for the customer long-term stable. So we've built up a lot of knowledge around recycling, reusing, improving on the material level, which also includes the permanent magnets that we are currently using as a magnetic field source. So also there we have shown that we can not only use and reuse the magnets because they're indefinitely performant, but also we can use recycled materials for the permanent magnet. So there are a lot of opportunities to have a circular economy approach with magnetocaloric cooling technology. And another benefit is that our operational level is around atmospheric pressure, actually a little bit below at the moment. So there's little stress on the components, which makes it also more long-term stable and can be reused.
And similar answer here for the barocalorics for Pascal. Our material is not exotic. We take components out of existing supply chains and then apply our proprietary processing techniques to those components. And it's a solid that is infinitely recyclable. And the way we've spoken to customers, that's something they really care about, is that embodied carbon of that material, and also the recycling processes that go along with it. So both the material is recyclable and reusable, and another additional benefit is our components. Because we use very similar components to what's already found in the existing HVAC supply chain, a lot of customers that we've spoken with, for example, if they're based in Europe, they are responsible by law to help with the recycling management of their items that they purchase, of their manufactured items. And so because we use a lot of the similar components, we can rely on a lot of the existing recycling supply chains and reuse supply chains that are already in place.
Right, thank you both. I think we also have Mark from Exergen and Berardo from Mimic. So the next question I can ask you guys if you're there. A question we have is the technologies that we're talking about here today are they cost competitive against incumbent vapor compression technologies? And Lindsay, you can also chip in here. Mark, maybe you can take the lead here, and then Berardo. Are you guys able to unmute yourselves?
Do you want me to go first, Selen,
Yes,
or do
you
you
go
want
right.
to wait for Mark?
Go for it.
Well, as Lindsay alluded during the webinar, semiconductor technologies, initially they tend to come with a little bit of premium. Sometimes, it happened to many in those fields. If you remember, for example, solar, it was very expensive at the beginning. Even LEDs, they were expensive. The reality is it's not a problem from material procurement perspective. Materials that we use are relatively cheap, relatively abundant. The reality is that the way that we process them needs some refinements. And so this is where we are actively working on. So initially, I think what we are taking a lot of emphasis is trying to understand how from a manufacturing and product development and technology development roadmap, we can reach cost parity or even cost effectiveness compared to traditional vapor compression systems, which are leveraging hundreds, many, many decades of optimizations from a manufacturing perspective. We know that this is a work that we have to do, but we don't see any technical barrier to become cost effective.
Thank you, Berardo. Lindsay, did you want to add anything here?
No, I honestly think Berardo covered that one perfectly. As we expect, climate technology is, like Berardo mentioned, HVAC manufacturers are leaning on a long time of cost optimization. They have their supply chains in place. They have manufacturing facilities like optimized to reduce cost. And so for these early stage startups coming in, of course, they're going to be slightly higher because they need to, go through the similar process in terms of optimization for cost, manufacturing at scale, et cetera. So yeah, I think Berardo covered it really well, and that probably holds for most of the technologies here too. Is starting at a slightly higher cost while you're getting established, building up manufacturing capability, optimizing your system from a cost perspective, and then will likely be closer to the cost of at market solutions.
Thank you. I don't think we have Mark here right now, so I'm going to move on to the next question. So we discuss the role of policy to help scale these technologies, but governments don't only work on policy. They can only be buyers. They can also be buyers themselves, and they're also building owners and operators at times. So the audience was curious about what the solutions that governments can work on as buyers, and I think Anastasia would be a great person to answer this with her background in procurement as well, sustainable procurement. So Anastasia, do you want to take this one?
Yeah, I'm happy to. So governments, especially around the world, own and operate and lease a massive amount of real estate. If you think of all of the schools and hospitals and universities, government buildings all around the world. And so, for example, in the US, the US federal government is the largest landlord in the world. And so it's a very interesting policy lever that can be pulled to support new green technologies, to really think about their own operational footprint and what they're doing themselves. So can you be buying and testing and helping new technologies come to market just through your own purchasing? And we've seen some great examples of this in other settings. I would love to see more of this sort of work happening with government buyers, and that can be at the federal level or national level or at the state or local level. I think there's some interest because these are building owners and operators who do think long term, who do think about not just the upfront cost, but the life cycle cost. And many of these technologies really come to, some of their benefits. They might be more expensive right now in the short term, but over longer term time periods, you're not dealing with having to replace the gases. You're dealing with fairly energy efficient processes, so you're not paying as much for energy, and so on and so forth. So, some of these benefits can be realized by the building owners and operators, and let's not forget the governments themselves can do a lot here. So there is some good guidance that's coming out. I can put it in the chat from the Sustainable Purchasing Leadership Council, and the UN Environment Program has put out some guidance here too. There's more that we can all do collectively on this front. And I'd be really excited to see more governments stepping up here and really encouraging their own use and thinking about their own use and taking some of that technology risk as governments, which they can do. Yeah.
Hi, thank you, Anastasia. So we actually have another question for Mimic while we have you on, Berardo. For the higher energy efficiency that thermoelectrics offers, what is the payback period for the higher cost, at least the upfront initial higher cost? We're curious about the payback.
So a very, very good question. It's really, really good question. It mostly depends on the jurisdictions where you work with, and the local energy cost. So the way that we look at the payback is effectively looking at the total cost of ownership. So how much does it cost you to the equipment itself? How much does it cost you to install? How much does it cost you to operate? And how much does it cost you to maintain? Interestingly enough, in some places, for example, in the US, even if you yield a lot, even if you are very, very efficient on an all-electric basis, for example, for heating and cooling, if we just look at the energy cost, most of the times or sometimes you're not even able to compete against the cost of natural gas or fossil fuel for heating. That is because the cost of electricity is significantly higher than the cost of natural gas. So even if you are more efficient, it doesn't mean that from a financial perspective you have a better economics. And so this is why I think probably goes back to some of my colleagues' approach to when they were talking about go-to-market strategy. We try to take into account also the maintenance costs and the long-term recurring costs. We factor those in. That is where we see that there are opportunities for us to be more efficient, from a deployment perspective. So that is the payback. Typically payback depends on the type of applications. We are looking at, in the built environment, we look at years in terms of payback. There are some customers that are even willing to entertain a 10-year payback because they own the properties and they manage and they run their properties. Staying within 3 to 5 years payback, it's a very good number in general.
Right. Thank you, Berardo. Timur, do you also want to chime in here on the payback?
Sure. So for us, it's also a combination of the invest costs and then the operational and running costs. So what we see from the commercial refrigeration space is that the refrigerant management incurs a lot of unknown costs because with the F-gas regulation, certain refrigerants will not be able to be sold anymore. So we see from supermarket chains that they are setting up consortia to actually manage the refrigerants, and those costs are currently not internalized. So even though we have very good energy efficiency, and also we can bring down the maintenance costs, there are even more costs that will be visible in the future. So when we approach a supermarket with a plug-in unit, our goal is to have a payback period after 2 to 3 years, with a higher energy efficiency, but also with zero maintenance costs over on the technology level. And with those trends kicking in, it's only getting better for us then.
Right. Thank you, Timur. We're coming up short on time, so I'll ask one last question, and then we'll move to concluding remarks. So we have a question on innovative finance mechanisms. Obviously, we realize there's a huge investment gap here, and we need all hands on deck, all kinds of different investment mechanisms on the table to help scale up these technologies. So perhaps Anastasia and Lindsay, you guys can talk about this a little bit. Are there any blended finance mechanisms out there that you know of that can de-risk investments, as well as the idea of advanced market commitments, if you know of any? Probably not on this on ACTs currently, not that we know of, but what is the potential? Do you see a big role for these types of innovative financing mechanisms here?
Lindsay, do you want to start?
Sure, happy to. I think, gosh, there's so much we could talk about in terms of finance here. So first things, a lot of these developers are like early stage, and that's where things like grant funding is really critical for scaling up research and development. Early venture capital as well from corporates like CVCs, as well as typical VCs can play a really important role. So I think I saw there was at least one climate tech investor that joined today. So that's maybe a nudge to you to explore this technology class. And then of course there's so many other financial pathways as we scale this up. So I think Anastasia, you can get to this more, but maybe just touching on the idea of an advanced market commitment. I maybe teed that up because I'm hoping it'll spur interest and maybe manifesting that a little bit. But I think there's a huge opportunity there, and this is where we can look at things like that are gaining momentum. So like a buyer's platform. RMI has launched buyer's platforms for steel, low carbon steel procurement, low carbon concrete procurement with really large procurers. And that is something that can help, one, signal demand and help provide financing that can reduce the cost of deployment. So it helps these startups scale up because they have that committed capital, that investment. And so that's definitely a platform and a mechanism that we would love to see in the active cooling space as well. So I'll pause there, but yeah, Anastasia, I would love your reflections too.
Yeah, I'm similarly excited about advanced market commitments. These are where buyers of, the goods or services say in advance, we will buy at this price. That really helps a startup in particular, but any company, honestly, that's trying to bring a new product to market, to have some certainty that there's a buyer on the other side that they know is going to buy and that they are going to receive that contract. That in turn allows them to raise money to pay for equipment, supplies, build their facilities, and leverage other financing like bank financing and loans and stuff if they have that contract. So this has been used very effectively in renewable energy financing. And I think there's many structures that could be used here as well. And then I'll just add two other thoughts on this. There's all sorts of government incentives and rebate type programs that have been really effective in getting things like heat pumps to market, or all sorts of energy efficiency technologies as well. So I think that could be a really great area for governments to start to incentivize the customer base, either individuals or households or the businesses, to take advantage of this technology and to encourage it. And then the third one I would say would be carbon credits. So, in some instances, you could think about generating a carbon credit to show the delta or the difference between replacing our old leaky high GWP gas system and replacing it with one of these super efficient solid state type systems. I don't know of a methodology written yet for to be able to do that, but that is something I think could work well for a limited period of time until these things are able to stand, on their own and compete head to head. So some ideas, but certainly an area that the CC Lab is really interested in exploring. And if you have ideas or thoughts or examples, we'd love to hear them as well. And we're very excited about RMI's work on the buyers platforms. So this is a good area, I think.
And thank you so much, both. So this was all we had time for the Q&A today. But if you have pressing, burning questions, you can always reach out to us. We'll share our emails again in the chat. So you can email me. I can collect all the other questions you have remaining. So with that, we'll move on to our concluding remarks. Anastasia?
Yeah, well, thank you. I just wanted to share a few thoughts in listening to these fantastic presentations and videos. Firstly, thank you for joining us today. Everyone who called in, thank you very much to the technology companies who very kindly made these videos for this webinar and really shared their technologies. We know you're very busy and this was very kind of you to share and open up and see a little bit of the technologies as well. So thank you for that. Thank you to RMI and CCAC for hosting and co-hosting and presenting today. As well, as you can tell, we're very excited about this topic, and so much so that we have another webinar. We felt that we could not squeeze it all into one. And so we have this time next week, we will go into hybrid and passive cooling technologies. And then the discussion will be on the role of international policy in bringing any and all of these to reach the scale of the potential that we've heard about today. So please do join us for that. And we will be sharing, the registration links and all of that. CCAC has done a fantastic job on that. And then final plug, if you could go to the next slide, I'll just mention that we are holding at Yale University in the US next year, March 5 and 6. We're going to have an expo of different technologies on both that support both refrigerant management and alternative cooling technologies. We'll have a webinar component. So for people joining from around the world, we will have some plenaries and some ability to join us online. But yeah, wanted to make sure you knew about that. If you're interested, there's the QR code and please join us for that. It's going to be really fun. Good gathering of all sorts of people from finance to companies to startups to policy, academia. So we're really bringing people together to think about this sort of cooling need and really transitioning out of this sort of sector that we've been in. So and the pathway that we've been in for the last sort of 100 years or so. So next slide. We are happy to stay in touch with you beyond these webinars. Here's Celine and my email address, but we'll share, the full team here that has been presenting today. And just a final note, this is a big sector. Lindsay gave some fantastic overview of just how big some of these markets are. This is a team sport, and there are roles for everybody in this. So we're really grateful that you're interested. We look forward to learning more what you're doing from all over the world. We're sure that our database is going to grow, and we invite you to keep sending good examples. We'd love to keep featuring more, especially from different parts of the world. So please let us know what you're seeing and hearing, or if you're involved in something yourself. We'd love to keep learning from each other and make this happen. So with that, thank you very much. Denise, did you want to say any words at the end here as well?
No, just to say that again, as asked by many of the participants as well, we will be circulating the slides towards the end using the circulation list of those that registered, as well as make the video available, but not by tomorrow, but soon we will have the video available, because there were some that were, it was a little bit difficult because of the time, but we're very, very also interested in watching and listening to the webinar. So we'll see all of you next week in part 2 of the webinar series.
Thank you, everybody. Thanks for joining.
Thank you. Bye, everybody.
Bye-bye. Thank you.
Thank you. Bye.